Till now, we discussed various ways of drawing the structure of molecules and we talked about Lewis structures. Lewis structure can give information about shared and unshared electrons, but it has some limitations. Lewis structure cannot explain the 3D geometry of the molecule. Also, it cannot describe where exactly the reactive electrons are located in the molecules, which is super important in this course to understand organic reactions. So, for this purpose, to understand the geometry and where the reactive electrons are, we need to focus on different theories that involve orbitals. In 1920s, chemists proposed a mathematical description of electrons that incorporate its wave-like properties. This theory was called quantum mechanics and changed the way that we view the nature of electrons and bonding. So classical mechanics, Lewis structure, failed to describe that before. We are not going to talk about the math here, but I want you to know the result of solving these equations. So there are three definitions here that I want you to focus on. The first one, I believe all of you know that, is this definition. The 3D space where electrons are allowed to be are called orbitals. So we call these 3D regions orbitals. The chance of finding electrons in this 3D region is about 90 to 95%. And the second definition is when you consider electrons in an atom, uh, we call those orbitals atomic orbitals. So atom itself have electrons in atomic orbitals. Solving the quantum mechanics equation shows that we have four different types of orbitals: s, p, d, and f. S orbital is spherical, as you can see here, and if electrons fill that s orbital, their movement is confined within this region, in this spherical region. We also have p orbitals. P orbital is dumbbell shaped, and we have three of them oriented along the three coordinates x, y, z. I'm gonna talk about them in the next slide. And we also have d and f orbitals. We are not gonna focus on d and f because in this course our main focus is on the first and second row elements, so we are not going to focus on d and f, but I want you to know s orbital, p orbitals, their shape, and their types. So the third definition, which is here, when atoms bind together to make a molecule, electrons now gonna be in molecular orbitals instead of atomic orbitals. So they are gonna occupy molecular orbitals. We are gonna talk about these orbitals later on. Before I talk more about atomic orbitals, I want you to know a definition here. I believe it might be new for some of you. So if you consider a wave on a lake, as a wave going up and down, it's gonna have some positive region and some negative regions. And there are some places that are basically in an exact level as the lake level. So there is no positive or negative here, and it is 0 point. Electrons also have a wave-like properties. Therefore, in the orbitals, we also have positive regions and negative regions. And when you move from positive to negative or from negative to positive, when you change the phases, you are going to have nodes. And the chance of finding electrons in the node region is 0. So electrons can be anywhere in here or anywhere in here, but not on the node. So as you can see, this is the 2p orbital, and 2p orbital has one node. And since we are also talking about s orbitals, one s orbital has 0 nodes and 2s orbital has one node. So we have a phase change in 2s orbital as well. I want to emphasize that this positive and negative sign, they do nothing with electrical charge. These signs, it is only for you guys to understand the phase change, to understand that this part of the orbital has a different phase comparing to this part of the orbital. These positive and negative signs, they are completely different from the positive and negative that we are using to show the charge on molecules. It is just showing the different phases on orbitals. Organic molecules are mostly composed of first and second row elements, so we are just going to focus on atomic orbitals in these atoms. And atomic orbitals here, if you remember from GenChem, the first row is occupying 1s orbital, the second one 2s, and then 2p orbitals. And here you can see the shape of these orbitals. 1s orbital, it has one phase, so 0 node. 2s, it has two phases, therefore it has one node, and 2p orbital clearly shows different phases, so all three has one node. These three orbitals, py, x, and z, they have same energy level. We call them degenerate orbitals. And if you want to compare the energy level of all of these orbitals, the 1s has lower energy comparing to 2s, and 2s comparing to 2p. And all of these three orbitals have same level of energy, so they are degenerate orbitals. Now, how do we fill these orbitals with electrons? The order in which orbitals are filled by electrons is determined by three principles. Alpha principle, that says the lowest energy orbital is filled first. So among the three orbitals, 1s is lowest in energy, so it fills up first. 2s is the next, and then 2p orbitals. The second principle is Pauli exclusion principle, which says that each orbital accommodates a maximum of 2 electrons that have opposite spin, one spin up and one spin down. So if you consider this as orbital, one electrons is a spin up, the other one is a spin down. And the third principle is Hund's rule. So if you have degenerate orbitals, you put electrons in each orbital first, and then you start pairing them up if it is needed. So if you look at the 2p orbitals, we have 3 2p orbitals, all of them are degenerate. So if you need to put electrons in these orbitals, you first need to fill each 2p orbitals first, and then start pairing them up if it is needed. Now let's focus on carbon atom. Here you need to look at the periodic table and find the atomic number. Pay attention that we are focusing on atomic number here, not the valence electron. So the carbon's atomic number is 6. So we have 6 electrons to fill the atomic orbitals. We start by putting first electron to 1s orbital based on alpha principle. Then next electron pair with the first one with opposite spin before we move to the next energy level. So I put the second electron here. Then we put the electrons in the 2s orbital. So I already used 4 electrons. Now I have 2 electrons to put in p orbitals, and based on Hund's rule, we first put them in each degenerate orbital, and then we are good because I used all 6 electrons for the carbon. If we put these information together, we can draw the same thing for common elements in row 1 and 2, the elements that we care about the most in this course. So if you look at hydrogen, the energy diagram for hydrogen, helium, lithium, um, beryllium, boron, carbon, nitrogen, and oxygen. And here is the part of the periodic table that I maximized for you so you can easily see the atomic number. The atomic number in this periodic table is written on top of each element symbol. So if you look at beryllium, for example, the beryllium atomic number is 4. So I have 4 electrons to put in atomic number. Again, I fill the 1s orbital, 1 spin up, and then 1 spin down. And then I fill out the 2s orbital, 1 up and 1 down. How about oxygen? The oxygen atomic number is 8, as you can see here. It is written on top of the symbol. So to fill out the atomic orbital, I need to put 8 electrons in this diagram. I will start with 1s orbital, 1 spin up, 1 spin down. 2s orbital is also the same, 1 up, 1 down. I already used 4 electrons. I have 4 more electrons to put in 2p orbital. Therefore, I first fill 3p orbitals first, and then to have 8 electrons, one of them should be paired. Now that we know electrons occupy atomic orbitals in an atom, we can think about how these orbitals can come together and make covalent bonds. Valence bond theory and molecular orbital theory are the tools that describe the nature of atomic orbitals overlap. So we first start with valence bond theory, or VBT. If we consider an electron as a wave, then we can study what will happen when 2 waves interact with each other. In the similar way, we can study what will happen when 2 atomic orbitals overlap with each other. Because we know that electrons are not only dots on a paper, they are in atomic orbitals, and these atomic orbitals can interact with each other. So we have 2 types of interference here. It can be constructive interference, and that happens when 2 waves are coming close to each other and they have same phase, or basically we call them in phase. Therefore, they will reinforce each other to make constructive interference. So the amplitude will be higher in constructive interference. In destructive interference, when 2 waves coming close to each other but they have different phases, or basically we call them out of phase, they are out of phase, they will cancel out each other, so we are going to have destructive interference. If 2 orbitals constructively overlap with each other, they share their electrons with each other and covalent bond can form. If you look at the hydrogen molecule here, there is a line between these 2 hydrogens, and this bond is formed as a result of constructive overlap between 1s orbital of one hydrogen and 1s orbital of another hydrogen to make the covalent bond. This shows the overlapping of orbitals, the constructive overlapping of orbitals. The single bond that is formed between these 2 hydrogens, in chemistry we call that single bond a sigma bond. So all single bonds are sigma bonds in chemistry. We draw the HH bond as a single bond on a paper as it is drawn here, but in the real world that single bond is actually a result of constructive overlap of two atomic orbitals. But on a paper we draw it like this instead of drawing the overlap of all orbitals, which is harder to draw. Sometimes valence bond theory cannot properly explain the bonding in molecules, so we use another theory which we call that molecular orbital theory or MO theory. The MO uses a mathematical tool called linear combination of atomic orbital or LCAO to describe bonding in molecules. We are not going to learn about the math in this course. It's beyond the concept of this course. And also I don't want you to learn how to draw the MO diagrams for all the molecules. What I want you to know is the concept of MO theory and being able to use it later on in this course. So I'm going to use the hydrogen molecule to describe the MO theory here. So each hydrogen in the hydrogen molecule has one atomic orbital, one s atomic orbital, and each atomic orbital is filled by one electron. We just talked about different interference in between the atomic orbitals, and we can have constructive or destructive interference here. The MO theory says that if these two atomic orbitals constructively interact with each other, they can make a molecular orbital that is lower in energy and therefore it is more stable, and we call that bonding MO. However, if these two atomic orbitals interact with each other destructively, they can make a molecular orbital which is higher in energy, less stable, and we call that anti-bonding MO. So MO says that after atomic orbitals overlap with each other, they stop to exist. So the electrons in atomic orbitals will occupy the bonding MO to achieve a lower energy state. And remember in chemistry, lower energy means stability. So the molecule becomes more stable. Therefore, these two electrons occupy the bonding MO. And basically we don't have these atomic orbitals anymore. We only have bonding MO and anti-bonding MO. These two MO orbitals belong to the whole molecule, and the electrons being in bonding molecular orbital can make a sigma bond between these two hydrogens. So we can have a sigma bond between these two hydrogens.